Hi everyone, welcome to this video. So in this video, we're gonna be talking about big omega notation format. So basically, big omega notation is one of the main types of asymptotic notations, which are being used in asymptotic analysis. So there are three main types of asymptotic notation. One is big O notation, which refers to worst case time complexity, and there is big omega notation, which refers to the best case time complexity of an algorithm, and there is big theta notation, which is an average case time complexity for an algorithm, and it is also a type 1. So in this video, we'll be talking about big omega notation, which refers to best case time complexity of an algorithm. Yeah, so let us start it. First, we shall see. First, we're gonna start this topic by understanding what is an algorithm efficiency. Yeah, so whenever we have a computation program, so we can have multiple approaches which will give rises to different types of algorithms. So when we have different algorithms, so how do we select an algorithm? So the way to select is in most cases the way to select is by analyzing the algorithm's efficiency. So we analyze the algorithm efficiency in terms of time complexity or in terms of space complexity. Yeah, so time complexity and space complexity, we are not interested in finding the exact concrete values of how much running time an algorithm takes, but instead we want to find the growth rate of an algorithm, growth rate of time complexity or growth rate of source complexity, which algorithm gonna take as the input size progresses. So mainly we are focusing mainly when for larger size of the inputs. So that is what we are algorithm efficiency is all about, is like analyzing time complexity and space complexity in terms of input size. Yeah, so this topic gives rises to all this asymptotic analysis notations. So in this video, we are going to check out what is big omega notation. Yeah, so what is big omega notation? So big omega notation is nothing but a lower bound of the time complexity of an algorithm. Lower bound of not only time complexity but also a space complexity. So an algorithm, if we have an algorithm for a given input size, what is the least time complexity the algorithm can take, which will be represented by this big omega notation. And we can say this is the way it will be commonly represented. This is the symbol we use, big omega of f of n. So here, this f of n function is the lower bound time complexity function. So suppose if we say an algorithm has a time complexity of big omega of f of n, it means that the algorithm's runtime will always be, or at least it will be, a constant multiple of this function f of n for sufficiently large input size. For sufficiently large input size means for larger input sizes, like for sizes which are like more than thousand, or more be sizes which are approaching infinity as well. So this is how we represent big omega notation. And suppose if we take let us take an example. Suppose if we say the algorithm has an time complexity of big omega of n log n, it means that the running time will be at least a constant multiple of n log n function for large size inputs. So this is what is big omega notation is about. Big omega notation tells us the lower bound of the time complexity for a given size of the input. So let us understand this by taking an example. So here I took the example of insertion sort algorithm. Yeah. So first, let me just give a quick overview of what is insertion sort is all about. So insertion sort is all about, as name suggests, it is a sorting algorithm. So here I'm giving an array as an input. So the idea of insertion sort is to sort the given array part by part. So it will start from the second element of the array, and it will go all the way to last element. So when we are in the second element, it will do the sorting for first two elements, and when it goes to the third element, it does the sorting for first three elements, and when it go to fourth element, it does the sorting for first four elements, and when it reaches the final element, it does the sorting for the whole array. So this is the concept of sorting algorithm is all about. So here is the computer program which is written in Java for this algorithm. So here we have two loops. The one loop which is traversing from second element of the array and all the way to last element, and inside this we have an inner loop which will traverse back from j minus 1 to all the way to the first element, and it will do the sorting algorithm. So here the sorting algorithm has a condition. So the condition is that in the given array, if we take any pair of consecutive elements only, if we take consecutive elements to the left of j, suppose if we are in j equals to 3 third position, or j equal to 4, it means the third position. Then if the to the all elements left to the array, if we take the pairs of consecutive elements, the left if left side value is of the pair is greater than right side value, then we'll enter this and do the swapping to do the sorting algorithm. So if not, we won't enter this. So let me just give a quick example. So first, if we look at this array, if as I said, it will start from the second element. So we'll do the compare of first these two elements. If left side value is greater than right side value, we'll do the swapping. So here, as it is left side value is greater than right side value, we'll enter this loop and we'll do the swapping. Yeah, so after that, we'll be incrementing on this outer loop and we'll be going to the next element. Next, we'll be doing the comparison of 53 and 54. As left side is greater than right side, we'll do the swapping, and the 35 will come here and 53 go here, and then we'll do the swapping of we'll do the check for 12 and 35. Here 12 and 35, the left side is less than right side, then we won't enter this loop. We'll just the loop will just stop this inner loop and we'll go to the next iteration of outer loop, and we'll go to the next element, and then we'll do the comparison of these two elements, then these two and this two. So the idea is that the elements left to this I position. So if we take if we create pairs of using this element, the left side value should be greater than right side value. So if it is not, here in the case that if left side is not greater than right side, we won't do the swapping and we won't enter this at all. So this is the idea of the instruction sort is all about. So basically, we'll be doing the sorting part by part, iteration by iteration. Yeah. So this is what instruction sort is all about. Now let us analyze the time complexity for this algorithm. So for doing time complexity, I have divided it into two different cases. So the first case is that if we are given an input, an array, which is already sorted in ascending order. If we assume this is the our input 1, 2, 3, 4, 5. So in this case, we won't be entering this inner loop at all, because if we take any pair of consecutive elements, we can see that the left side value is not greater than right side value at any point of time. So due to this, we won't enter this inner loop at all. So due to this, we will only enter this outer loop. We will be executing this line and this line as number of times as the size of input, and will be returning the array. So the time complexity will be of time will be order of n. So the time complexity only grows linearly with the input size when input is already sorted array in ascending order. Now we shall move on to the case 2. The case 2 is that if input array is if input is already a sorted list or an array in descending order. In this case, if we assume this is an input array 5, 4, 3, 2, 1. In this case, if we take an pair of consecutive elements, every time the left side value is greater than right side value. So for all values, this outer loop j can point to. There will be one case where input left side value will be greater than right side value, then we'll be entering this. So when we are in the first element, we'll be doing swapping for we'll be doing one swap, and when we are in the second element, we'll be doing one swap. When we are in third element, we'll be doing two swaps, like this. And when we are in the last element, we'll be doing n minus two swaps, n being the size of element. So if we calculate the number of times these instructions will be evaluated, it will be like this n square by 2 plus n by 2 minus 2. Basically, it will be order of square of the input size. So in this case, the time complexity grows in order of size of in order of square of input size. So here, as we can see, right, based on complexion of input, the time complexity of the same algorithm is different. If input is a sorted array in ascending order, the time complexity is in order of n. If input is of of type descending order, the time complexity is of type is of order of square of input size. If you plot a graph of these two functions, it will be like this. The only portion of the graph which we really care about is the this part after x equals to 0, only the positive x part, because size of input cannot be less than, cannot be a negative value, right? So here we can say that this is the upper bound of our time complexity, and this is the lower bound of time complexity. The meaning is that, suppose if we take n equals to 5, if suppose if input size is 5, the minimum time it can take to complete the instructions can be given by this can be by calculating the value of this y equal to x. It is being that 5. So if you want to find the maximum value the algorithm will take, or maximum instructions the algorithm will take to complete the algorithm, will be given by this. So the maximum value will be given by this, and minimum value will be given by this. So we can say that this is the upper bound and this is the lower bound of time complexity. So the time complexity can be anything between these two. Yeah, so we can say that this y equal to x is the lower bound for most of the part in uh, positive x-axis, but there is from x equal to 0 to x equal to 3, the straight line is dominating the curve, but here it is only two instances, right? N equals to one size and n equals to two size, so it won't matter. So the for most of part in positive x-axis, the y equal to x is the lower bound. So since we have said that big notation is all about the lower bound time complexity, so we will be using this n as an expression in our big omega notation. So basically, because n square, this quadratic equation acts as upper bound and n acts as lower bound. So this is what the lower bound and upper bound is all about. So we'll be using this lower bound for big omega notation. So in this case, based on time input complexion, the time complexity is different. We have a lower bound and we have upper bound. There are some cases in which the time complexity won't depend on the type of input, but it only depends on size. So some of the examples are some this algorithm, some of elements of an array. In this algorithm, it will take the array as input, and here I'm looping through this array, and I'm adding all the numbers and returning the array. So here, whatever might be the complexion of array, we'll be definitely running this loop and we'll be doing the sum. So these instructions will be ran as number of times as the size of this array. So we can say that the time complexity is of order of n. So this is the upper one and this is the lower one, nothing else. So here we can say that big omega of n is the time complexity of this one. So this is and which is also lower bound and also upper bound as well. Similarly, if we see this algorithm finding pairs, finding all possible pairs of an array, here we have two loops. One is from running from 0 to last element, other is running from I plus 1 to last element. And when we are finding the pair, we are adding to the list. Here as well, whatever might be the complexion of array, we'll be creating a loop for based on combination of I and j, and we will be creating this pair and add it to the list. Here as well, it will be order of These instructions will be ran in the order of square of this input size. So we can say that the time complexity is like big omega of n square, which is the lower limit, and also this is upper limit as well. Big O of n square and big omega of n square, both are same. Best case is same and worst case is also same. So this is what is big omega is all about. So basically, big omega is nothing but an expression which gives us the minimum time complexity for most of the input sizes, mainly for larger input sizes, because we do an asymptotic analysis. So what is an asymptotic analysis? Since we have understood big omega, now we will see what is asymptotic analysis. So, asymptotic analysis of an algorithm is nothing but the study of how algorithms efficiency means time complexity, algorithm time complexity or space complexity behaves when input size is approaching infinity. So, the study of algorithms time complexity or space complexity when input size is reaching infinity is all about asymptotic analysis. So let us first check out some common names in this concept. So one such name is asymptotically positive function. So a function is said to be asymptotically positive if there exists a positive variable n naught, after which the values of the function is should be greater than zero. So, in simple words, we can say that the f of n should be greater than 0 after a certain point called n equal to n naught. Then we can say that this function is asymptotically positive. So, some of the example of asymptotically positive are this quadratic equation n square minus 2n plus plus 70. This is positive after a certain n equal to n naught, right? So this is asymptotically positive. Similar case of 2n for 10, and in the case of n square minus n cube plus 2, this after x-axis itself, it will be mostly going to negative y-axis. So this is not asymptotically positive. Yeah, so basically we'll only consider asymptotically positive function as a time complexity for an algorithm, because time complexity cannot be negative, right? Yeah. So this is what asymptotically positive function is about. Now we will see how to calculate the time complexity in big omega notation for an algorithm. So for that we'll be following these steps. The first step is to express the lower bound time complexity or space complexity uh, of the given algorithm in the terms of input size. Let us say as n. So let us do this, determine the big omega notation time complexity for the first example which I have seen, which is instruction float. For this we have seen n is the lower bound time complexity, and this quadratic equation is the upper bound time complexity. So we have to use this lower bound time complexity, which is n, to determine the big omega notation for this time complexity. And then the second step is to we have to identify the dominant term in the function, which grows faster as an input size is reaching infinity. So in this case, we have the only one term which is n. So which grows, definitely it is the dominant term as it is only term, and it is in the third term it is saying to drop constant factors or lower order term, since it is the only term, we don't need to drop anything. So the resultant will be the expression in big omega notation. So in this case, the time complexity in big omega notation for insertion slot algorithm is big omega of n. So this is how to determine time complexity in big omega notation. In other words, we can say this is the lower bound time complexity of an algorithm when input size is reaching infinity, or else we can say for larger input size. Yeah. So this is what big omega notation, how to determine big omega notation. Now since we know big omega notation is itself is an asymptotic notation, um, it big omega, the expression in big omega doesn't tell the exact time complexity of an algorithm. Here let us say here we are saying that the time complexity of instruction slot in big omega is big omega of n, right? So this n doesn't give the time complexity of this algorithm at all. So it only gives the lower value a this algorithm can take for a certain value of n. Suppose if we assume n equals to 2, for n equals to 2, this expression value is 2, right? So it doesn't mean that after two instructions this algorithm will be done. It only gives that for n equals to 2, the minimum steps it can take for a particular type of input complexion, it is 2. So, as we already talked about, it has lower bound and upper bound time complexity. For n equals to 2, the lower value which it can take is by this expression n. The highest value it can take is like this n square. If we calculate to give it 2, it will be like 4 by 2 plus 2 1, and it will be like 4 basically. So this gives us value 2 and this gives us value 4. So the lower value, the lower number of instructions which can complete this, which can take to complete this algorithm is 2. Then the highest number of instructions which the algorithm takes to complete the um, execution of algorithm for input size 2 is 4. So basically this is the maximum instructions it can take, and this is the lower instructions, low minimum instructions it will take. So it can take any value from 2 to 4. It can be 3 or 2 or 4. So that is the concept of it. So the big omega notation does not tell the exact time complexity, but it only tells the minimum time complexity, or else the lower bound time complexity for input sizes which are all larger. Yeah, so we can. This is a common way of representing a lower bound time complexity for a function. Let us say f of n. So here, f of n is nothing but the running time complexity or space time complexity of an algorithm, and g of n being is the lower bound time complexity. Here, what does this means is f of n will be the value of f of n will be at least a constant multiple of g of n. Yeah, so g of n is lower bound and f of n is g of n. See, in other words, we can say f of n belongs to big of g of n if there exist two positive variables c and n naught, such that this inequality holds true. F of n should be greater than or equals to a constant multiple of g of n after a particular point called n naught. So basically, in simple terms, we can say that f of n should at least be a constant multiple of n naught after a certain constant called n equal to n naught. Then, if it holds true, then we can say that this f of n belongs to big omega of g of n. So let us understand this with an example. Here we can see how here f of n is like 3n square plus 2n plus 1. I'm saying I want to check whether it belongs to big omega of n square. Here we can see that this inequality of n greater than or equals to c, constant multiple of g of n, satisfies for c equals to 1 or 2 or 3, and n can be greater than 0. So this is the n naught and c can be these values. So here is a proof for when n equals to greater than 0, this inequality will definitely hold true. It is that I will be removing these two. So 3n square plus 2n plus 1 will always be greater than 3n square, always be greater than 2n square, and will always be greater than n square for n equal to greater than equal to 0. So we can say that f of n is always greater than equals to 3 dot g of n and 2 dot g of n g of n. So this inequality holds true for these values. So we can say that this expression is correct. Yeah. So this is this is what how we normally express lower bound for a function f of n. So here we are saying that normally we won't denote as like this f of n belonging to big of g of n. So normally if you see any textbooks or books, it will be denoted as this. So we use f of n equals to big omega of g of n instead of this belongs to function. So basically, this expression we can write it as equals to by removing this. Here, the case is that this is just a convention. So the equality here doesn't mean it is symmetric. It does. So the meaning is that this value is equals to big omega of z1. So, but this expression is wrong. Big omega of n square, we can't, it is not equals to this one. Let us understand this with an analogy. If I say Kiran is a human, it doesn't mean that a human is Kiran. This statement is wrong because human is a collection of species, right? Here as well, this big omega of n square is a collection of species. This is one of the value of this. So, if we say it as this, it will be the only value of this, right? It is not the case, but this can be the one of the values. So this is just a convention of this, doesn't mean. So here the equality is asymmetric. Yeah, so this is what how we commonly represent the lower bound for a function, let us say of n. And we'll see this theorem as well. The theorem is such as, if we say f of n equals to big omega of big O of g of n, it will also say that g of n equals to big omega of g of n. Meaning that here this, what does f of n this tells us about? It tells us that g of n is the upper bound of f of n. Meaning that f of n will be at most or a constant multiple of g of n. So since it will be at most, so it can also say that f of n is the lower bound of g of n and g of n is the upper bound of f of n. So if we say if f of n equals to big omega big O of g of n, it will also imply that g of n is like big omega of f of n. Yeah, so this is one of the theorem which we need to be keep a note of. Yeah, so this is what we have seen till now. We have seen what is a big omega notation, which is nothing but lower bound time complexity. We have seen two examples to understand it better way. We have seen insertion sort example and some sum of array and finding place example. So, and we understood what is big omega notation, and then we have seen what is asymptotic analysis, and we have seen what is asymptotically positive functions, and after that then we have seen the steps to calculate the time complexity of an algorithm in big omega notation. And then we have seen a general way of representing the asymptotic lower bound function for a, let us say, a given function called f of n. And then at the end we have seen a theorem as well. Yeah, so this is what this video is about. Yeah, thank you for watching. See you in the next.